I missed. So we're looking at what's the advantage of high pressure systems? Why do we go to 4 or 5 or even 6,000 PSI systems? What ultimately is the goal with hydraulics? What are we getting? I mean, what? It moves something using what? What do I do to move something? What do I have to apply? Is it pressure that moves something? Force, right? Actuators turn pressure into force. Okay? So the force is, what is our fluid measured in? What's the pressure? When I say it's 3, 4, 5,000, what is it? 3, 4, 5,000 what? PSI, or pounds per square inch, right? Okay. Equals, that's our pressure, right? But to move something, we need a certain amount of force. We need pounds. Okay? So inside an actuator, what do? We push that pressure against what? I'm going to do a square actuator because it makes the math a lot easier. So let's say I have, can those of you on that side of the room see this okay? The screen doesn't block it? Okay. So say I have a square actuator, say it's 10 inches per side. How many square inches is that? That's 100 square inches, right? So let's say I put 3,000 PSI, right? 3,000 pounds per square inch on 100 square inches. This is going to be a really big number. Most of our actuators aren't even close to this big. They're usually about that big, okay? So 3,000, I'm just writing it down here so it doesn't run into stuff, pounds per inch squared, pounds per square inch, times 100 inches, okay? What happens to our units here? They cancel, right? This one's below the line, this one's above the line. This would be inches over 1, essentially, right? If you're looking at that. So these cancel. So we end up in this case with 3, 2, 3, add a couple more zeros, 300,000 pounds. It's a lot of force. There's not too many things on the airplane that weigh 300,000 pounds. Maybe this would be happening in a jack or something, but okay. So say we need 300,000 pounds, but we don't want a giant 10 by 10 actuator, right? We want to make it smaller. Well, how can we make it smaller? What do we have to do to our pressure? Increase it. Say I want it to be, let's go with 6,000. Or say we want to reduce that in half. Say we want to go to 50 square inches, right? Square root of 50 is 2.2 or so times 2.2 inches or so per side, right? Square root of 50. Yeah, something like that. No, more than that. 7.0, I was way off. I was thinking 5 instead of 50. So 7.07. So say we want to make our actuator smaller. Well, what we can do is say we have, we need 300,000 pounds, but we only want to use 50 inches. So we divide that by 50 square inches, right? An actuator that's a quarter this size. No, it'd be half this size. Okay? That would equal 6,000 PSI, right? So we can go to a smaller actuator. That's why we're going to these higher pressure systems. What's the advantage of a smaller actuator? It's what? It's less weight and it takes up less space. It's lighter. So you can go to 3, 4, or 5,000 PSI systems and build the actuators smaller. Okay. What's allowed that is, as you make an actuator smaller, you have to have more precision manufacturing and better seals and that kind of thing. Technology allows that to happen nowadays. Okay, so that's where you're seeing this shift from the lower pressure to the higher pressure. Although again, the majority of planes today still are 3,000 PSI. It's really only your newest aircraft. Triple or 787, A350, that you're seeing these higher pressures. Okay. So that's kind of our tour of that and why they've gone smaller. Today, now we're going to get into the components now, these individual components. So the first one is pressure. We need pressure. So pressure is our pump is, its job is to take mechanical energy, typically in the form of spinning. Although, some of them do create a linear motion, like a hand pump, right? That's a linear motion, but some kind of mechanical energy, which can come from different sources. Where can our mechanical energy, what can make the pump spin? What did we say our two pumps were that were on the diagram a minute ago? Engine, which is taking fuel and turning it into mechanical energy. Okay? Or an electric motor is taking electricity and turning it into mechanical spinning energy. And we put that into the pump. So, we have some airplanes have hand pumps. If you go on the 727 in the cockpit, you look into the floor, there's 3 little panels you can open. And there are hand pumps in there to lower the landing gear if the hydraulic system fails, if the hydraulic pumps fail. In smaller airplanes, you probably saw vane and gear type pumps. We still use these sometimes, but vane and gear pumps are constant flow. They typically don't have a way to adjust the flow. And so they're not appropriate for our systems. So what we have is axial piston pumps, and these are typically used in systems greater than 1,500 PSI. They're variable displacement. They can vary how much fluid flow they have, but they try to maintain a constant pressure. And so actually have a couple of them here that I'm going to show you. That's why I've got all these boxes here. This is looking like a bad situation. Looking at these, a few details with them and things that are important. These piston pumps are not necessarily self-priming. That means if they're full of air, they're going to struggle to get that air out of them and start sucking fluid in. And so we need some way of helping to get fluid flowing into the pump initially. 2 ways this can be done. One is, you'll see on the examples I have here, there really isn't any it's just the piston pump. The example I have on the board, there's an impeller here at the inlet, which is a centrifugal type pump, and those are self-priming. And neither of these ones sitting here on the table have the centrifugal pump. And so that centrifugal pump or impeller can be used to get fluid moving up. It comes off the ends into the diffuser area and then gets brought in, and here, it can flow in here. This is where the pistons are being pulled back. And then as this cylinder block rotates, the piston's being pushed forward and fluid gets pushed out under pressure through the outlet. Okay? You can also see a certain amount of fluid passes out they call it this foot valve here. That's what's filling and going through this case drain, cooling the pump shaft, lubricating everything in here. That's that outer case. And then the cooling, they call this cooling flow, is our case drain line at the top. Okay, so again, that's not coming out under particularly high pressure. With these pumps that I have on the table, they don't have this integral impeller in them. What they use is they have a reservoir in the system that supplies bootstrap pressure. And bootstrap pressure is a small amount of pressure put on the fluid to get it to move from the reservoir to the pump. When we get to reservoirs, there's 3 different ways that can be done. We'll look at those 3 different methods for supplying bootstrap pressure. When you see these installed, here's an example of an engine-driven pump. You can see it looks very similar to the electric pumps I have sitting on the table. Right? They just, instead of being mounted to an electric motor, they're mounted to the gearbox. In fact, this is the one off our JT9 over in Hangar 1. So here is The biggest line coming to it is our inlet. We want to make sure it's got plenty of fluid coming to it, just like the biggest line on this one on the table is the inlet. Okay. We've got our the medium-sized line. That's the pressurized fluid coming out here on the left. And then the case drain on the right over here. Going back to the heat exchanger in order to provide the cooling. So same setup as the one inlet, outlet, and case drain. Okay. Now, the other thing you'll see I mentioned is, on this one that's on the table, I said there's a little drain line on the bottom in case the pump seals start to fail. This has it as well. On here, though, it's part of the gearbox. It's a little line that comes in right here. So if fluid leaks out of this pump into here, rather than getting forced into the gearbox, there's a little drain off the bottom, and it goes down and just drains out the bottom of the cowling. It also is to prevent fire hazard. But there is still electrical going to this. You'll see this here. Any idea what that might be? Temperature? You think it's temperature, or what's probably pressure? Okay. You've operated the hydraulics in the 727, right? That are electric pumps. They have the same kind of a setup as well. But if the pump is supposed to be on and there's no pressure being sensed, this will turn on an indication light in the flight deck. Okay. Or a message on ICAS. On many of these pumps, these engine-driven pumps, they also have something called a depressurization solenoid. And this is when you have one of these, if you need to shut this pump off while the engine's running, there is no physical way to actually do that, to disconnect it. But what we can do is essentially open a valve between the inlet and the pressure side and essentially stop fluid flow through the pump. And it will, it'll no longer produce pressure, but the pump will still be spinning. And there's still fluid hopefully going to the case drain, but it's not getting the flow that it's supposed to, and there's a limit to how long these things can run in that bypassed state, where they will cause damage from being rotated. Here's another AC motor pump. You can see the electric motor, similar to the one that's here. These are air-cooled electric motors. They've got fins on them. Okay, they've got fins. This one, like the one on the table here, has got a fan in the back of it that pulls air across there. This one, the fan's over on the right. It's integral with it. And driving a hydraulic pump. And if the picture really showed it, we have an intake or a supply, a pressure, and a case drain line coming off. And then this one's got a little drain line at the bottom as well. Okay. So one style, a couple others. Here's some bigger ones in the 727. Kind of down in the bay. You looked at these during your scavenger hunt. You can see they're kind of tucked in there. And you see how this is, at an angle right here. That looks very similar to this one that I've got right here, right? So that angled area is where that variable block or variable splash plate is located. Here's our case drain. I want to say that's inlet and that's pressure right there. Supply and pressure on the right. These pumps can also be driven other ways. So it's not just engine driven or hydraulic or electric motor. Those are the two most common ways they can be driven. But they can also be attached to an air turbine. And we can take bleed air. We take a little bit of bleed air and we run it through a turbine. And that can drive a hydraulic pump. Okay, it's typically a turbine. There's a gearbox, because that's going to spin pretty fast, and then it's going to be geared down to see it. You can see this pump on here, too. It's got one of these little dome thingies on it, just above the hydraulic pump arrow. Looks similar to the dome thing on here. Okay, that's going to, it's called an attenuator, and it's to smooth out those little, you'll get tiny little pressure dips and spikes, as each piston goes by. Right? These aren't perfectly smooth flow. It's not like a gear pump even a gear pump does it because the space is between the gears. There's always a bit of a pulsing. And so that attenuator, shown on here right above the arrow, or on the front of this pump right here, that's going to smooth out those little pulses you get from each piston every time a piston goes by and does a shot of fluid. Okay. Not all pumps have them. In a lot of cases, they don't. And if it's not critical to the system, then they don't put them on. In emergency situations, we can also drive these using a ram air turbine, so a rat hydraulic pump. So we talked about ram air turbines when we had electrical, and when we drove, we can drive a backup or an emergency generator using a rat. Rather than hooking it to a generator, we can also marry that ram air turbine directly to a hydraulic pump. You can see it's not a great picture, it's old, kind of grainy, but there are the hydraulic lines coming off the right side, off the back of this hydraulic pump here, that travel up the strut and back to the airplane in order to provide pressure. Okay. Got some detail of the different parts. So again, the outlet's going to be your pressure out to the system. Inlet's your supply, that suction coming in from the reservoir. Okay. What's going to be on the pressure side before it goes out to the rest of the system? What's it going to run through? It's going to run through a filter, remember. Okay. Case drain, cooling and lubricating the pump, needs to be cooled, filtered, and also returned to the reservoir. Okay. Another method we have for getting hydraulic pressure is we can use one hydraulic system to power a second hydraulic system. And we have something called a power transfer unit. So a hydraulic pump can also work as a motor. If you send fluid pressure in, you can actually make these things spin essentially make them spin by sending pressure. It's kind of like a generator can also, generator and a starter can kind of be the same thing. You can do the same thing with a hydraulic pump in many cases, not all of them. But when we're doing labs, when you guys are working on the 727, when you pressurize hydraulic system A, you open an interconnect valve. And that's real old school. You don't see that anymore. So when you pressurize hydraulic system B with the electric motor pumps, AC motor pumps, then you get pressure in system B, and in order to pressurize system A, we open a valve, and that pressure, that fluid is going right into system A. What's the downside to that? What can that lead to? What happens now? You've essentially gone from how many hydraulic systems to how many hydraulic systems? You've gone from 2 to 1, so you've lost some of that backup. What if there's a leak in the A hydraulic system and you open that interconnect? You lose pressure in A and you reach down and flip the interconnect to try to get pressure back, and you lost pressure because you lost fluid. Now what's going to happen to your system B fluid? You'll lose that as well. So you can see why they don't do that anymore. So starting with the 737 and Airbus, I don't know when they went to using these, but starting with the 737, they replaced that interconnect valve with one of these power transfer units. And I've got one here in my box of cool stuff. This one is still got some fluid associated with it. Try not to make too big a mess. Okay. So you essentially have two. Anyone want a handshake? I brought towels for a reason. So you've got two pump motors here. Yes, these do use Skydraw, by the way. This is phosphate ester fluid. You can see they've got purple data tags on them, purple fittings. Actually, that one doesn't have purple fittings, but okay. So here we've got a power transfer unit. On each side, you essentially have a motor, a hydraulic motor slash pump. Okay, they've got 3 ports, just like a hydraulic pump. So you've got a suction side as your large port. When it's operating as a pump, you've got your pressure side as the medium port. They each have a case drain. And then if one seal start leaking into the junction area, you've got a drain here sticking up that is a seal. A seal failed. If a seal fails, you can drain that area. The ones shown on the board here, you can see one on the left, one on the right. These ones don't actually have a case drain on them. Okay, they're a design that doesn't use a case drain. They do still have a drain between the pump and motor at the bottom, this little line, in case, again, in case the shaft seals leak here or here, it'll keep this cavity in the middle from filling up with fluid, and that's gonna just drain overboard. So if you go up to a plane, you see one of these drains dripping hydraulic fluid, it tells you the seals have gone bad in one of these pumps or motors, okay? But some are unidirectional. That means one side is always the motor, one side's always the pump. If there's a reason that one side is more critical, then you would want to have that. If one side is more flight control related or something along those lines. But the big key is there's no fluid exchange like there is with the interconnect valve that the older airplanes used. I've got another picture of one here. Okay, there's the one in our 727 and its installed state. Okay, this one is a directional one. So yes, the 727 does use one as well. This is in the standby system now, not in the main systems, not in A or B. But here is a hydraulic motor on one side, okay, hydraulic pump on the other. And so power can be transferred from the system this is hooked up to on the left to the system on the right. However, there's no fluid transfer. Next components we're going to look at are our reservoirs. And so the main job of the reservoir is to contain the hydraulic fluid. The majority of the fluid, we've got fluid out in the system, but we've got to maintain a certain amount in there. In theory, if nothing moved, you might be able to just have a pump and lines and everything without a reservoir. But what happens during operation, our total system volume changes. As we move actuators and other stuff like that, there's going to be a need for more and less fluid out in the actual system. And so we have to have a place for that extra fluid to be stored when it's not needed, and for that fluid to for that fluid to come from when it is needed. So that's where this compensating for changes in the volume of a system. The other thing that happens is temperature changes. As these systems run, they're going to heat up. And what happens to our hydraulic fluid as they heat up? What do fluids and other stuff do when they heat up? They're going to expand, and so they're going to need a place for that extra fluid to go. When they cool back down, that fluid will contract, and so you want to have extra fluid so that you don't run short in the system. The third thing they do is provide head pressure or bootstrap pressure, and this is what I was talking about with the pumps. If a pump is not self-priming, if it doesn't have that impeller system on it, we've got to make sure we maintain positive fluid flow to the pump. And so our reservoirs are typically pressurized in that regard. The other thing they'll do is bootstrap pressure helps prevent hydraulic fluid foaming. Why are we concerned about fluid foaming? What's the environment these things are operating in? What happens to the environment that they're operating in? What happens as the plane climbs? It's colder, okay. What else? What? The pressure drops. What happens when pressure drops with a fluid? It used to be I'd look around, someone would have a pop I could crack open, but nobody actually has anything carbonated today. So the hydraulic fluid gets a certain amount of air mixed into it from being actuated. And as you go up in altitude, it becomes more likely to foam. Okay, those air bubbles or that air will work its way out. And so by keeping a certain amount of pressure on the reservoir, it helps prevent that fluid from foaming. How do you think foam works when it gets sucked into a pump or pushed into a hydraulic system? It's very compressible. It's very squishy. It really doesn't work as hydraulic fluid at all. Okay, it suddenly can't produce any kind of force. It can't actuate things. So we want to make sure that our fluid doesn't foam. And so by keeping a constant pressure on it, we're able to prevent that from happening. Okay. So we're going to go ahead and take a break. When we come back from break, I'll show you the different types of reservoirs and kind of talk about how they work to maintain that head pressure.